Hello, I'd like to continue our adventure on day 2 of looking at linear systems. So I'd like to focus on matrix algebra first, and then look at some Matlab examples of those matrix algebra tidbits, and then have a look at our first linear system. So I'd shown you guys this before. These are field axioms. And we feel comfortable about these axioms with respect to real numbers, and we often think of it as somewhat trivial that you even talk about them. But it's a good foundational thing to see if they exist in other applications, like we talked about with floating point numbers, and we looked at how these apply or not apply in that case. For example, closure didn't apply. We didn't have closure for floating point numbers because floating point numbers is a finite number of numbers. So that's the reason there. But with respect to matrices, we want to look at what aspects do sort of apply for matrices, and it's pretty interesting to think of it from that perspective. So first of all, matrix algebra, when you add two matrices, say you've got a matrix A, matrix B, when you add two matrices, you get a third matrix. The matrices have to have the same size when you add them. So here I've shown 3 by 3, 3 by 3, but whatever A is, whatever the size of the A matrix is, the B matrix has to be the same size, and it's really just element by element, like you see A11 and B11, those add together, element by element, they add together, and that's matrix algebra from an addition perspective. And I think it's easy to see that since it's element by element, that it's going to be commutative. In other words, if we swapped and we put B first and we did B plus A, it's going to be the same thing. And since we're looking at element, and we're talking about these elements being real in this case, it's going to be associative as well. But again, obviously, these matrices have to have the same size in order to add them. Okay, so now the next thing is, now that we've kind of gotten the addition kind of squared away, there's this notion of scalar multiples. So you can take a scalar and scale the whole matrix, and what that means is you take the scalar and you basically scale each of the elements of that matrix. So, you know, whatever the original matrix is, the result's going to be the same size, and that's going to take care of that. So that's really pretty straightforward, the scalar multiple thing. And if we look at a scalar being -1, for example, lambda I've shown as, hey, if you have a scalar of -1, then straight away you see that you're going to get what they call the additive inverse. So the additive inverse would be taking your original matrix and multiplying it by -1. And when you add them together, you're going to get the zero matrix where every element is 0. So kind of going back to the original one, you know, we see for addition, you're going to have associativity, you're going to have commutativity, and you're going to see that you have an additive identity that's going to be all zeros, and you're going to see that you have an additive inverse, and it shows you how to get that. So we have that kind of already squared away just on that first slide. So that's matrix algebra, and it's focusing on addition. And obviously the zero is going to be the same size as the original A, and really you're just adding them once you have that. Okay, let's take a look at multiplication. Almost always when you hear the term matrix multiplication, it is a completely different animal than matrix addition. It is not element by element. It is not commutative. It is associative. There are size constraints on the multiplication of two matrices, and what happens is you're looking at taking a left-hand row and dotting it with a right-hand column. So what I've just done is I've shown you that you're going to take first row, A11, A12, A13, and you're going to multiply it or dot it with B11, B21, and B31. And the result, first row, first column, is going to be A11 times B11 plus A12 times B21 plus A13 times B31, or as I say colloquially, the first row dotted into the first column gives the first row, first column result. Let's try a different combination. Before I do that, you may have already picked up on my notation over here on the left-hand side. I use A, and then here the 3 is for the row, and the 1 is for the column. And same thing for the B. So it looks like, B, and then the subscript is row, column. So that kind of helps navigate how we put these things together. Okay, let's take a different combination. Let's say third row, dotted into first column. That should give the third row, first column entry in the result. Let's check it out. So using our notation, we've got 3, 1, 3, 2, 3, 3 for our A, dotted with a 1, 1, 2, 1, 3, 1 with our B. So that's going to be A31, B11 plus A32, B21 plus A33, B31 dotted together. Say here that R equals 3, and let's say here that that's the third row, and let's say here C equals 1, that's the first column. And if you notice over here in the dot product, the R is the same throughout, and the C is the same throughout. And what's happening is there's an indexing of the column of A and the row of B. If you notice, that's what's happening, and that same type of thing happens for any of the elements. You have this indexing, and it basically says that the left side column count, number of columns on the left, has to be the same as the right hand row count. And you're basically indexing through those multiplications, and then you sum them all together, and that's your end result. So that's kind of how it works. You have these constraints to kind of think of, and that's how matrix multiplication works. For matrix multiplication, there is this notion of multiplicative identity. It is a diagonal matrix I, called I, that has ones along its diagonal and zeros everywhere else. In this case, it's a 3 by 3. If our A looks like that, a 3 by 3. And for the multiplicative inverse, what that is this matrix called A to the minus 1, or A inverse. That is the multiplicative inverse of A if the product of A and A inverse is the identity matrix. So you have to have a square matrix for that. That means that the number of rows equals the number of columns. That's the only way that you get the square multiplicative identity on the right-hand side. It's very important to note that not all square A's have inverses. For a given A, if A inverse exists, then A is said to be invertible. Otherwise, A is singular. The distributive property for matrices, multiplication over addition, looks like this. There's two different ways, so it does seem to work. Go back and look at the original axioms that I showed you earlier. We have pretty much everything there, so it's important to review that and try to see how that works for matrices. Some other things that we have with matrix algebra is we have this notion of transpose, and that's simply where you take the previous rows and make them the new columns. So the A1 row, A11, A12, A13 becomes the first column, A11, A12, A13. So it's really a row for column swap. And the thing about that is that the diagonals will remain the same. So it's the off diagonals that actually get swapped. As you see, the 1, 3 here goes into the new position, 1, 3 there. What was at 3, 1 becomes the upper right position now. And that's denoted with a capital T for the transpose. And I would like to mention now, while I'm on the subject, if you have a product that is subsequently transposed, product of two matrices, subsequently transposed, it's equal to, you basically reverse the order of whatever product that you would have had there. So AB quantity transpose is B transpose times A transpose. And that same notion of how that sort of works with the inverse operator too. Like if you have two matrices whose product happens to be a square, its inverse is equal to the second one squared, the second one inverted times the first one inverted. Okay, without further ado, let's take a look at some Matlab. I've put some matrices in. I've got a capital A matrix defined, 3 by 3, as you see. First thing I'm going to do is look at the additive inverse. I'm going to say A1 equals, and let me do it like this, minus 1 times A. See if that works. Yeah, and then if I say A plus A1, what's that equal? Yeah, that equals the 0 matrix. So that using the minus 1 as the scalar on the matrix shows the additive inverse quite nicely. Now, taking a look at clear command, taking a look again at my A matrix, it looks like that. And then if I were to take maybe a second scalar, let me call it A10. So I'm going to say that's 10 times A. So I've got that second scalar multiple example. So it looks like that. And you know what? That looks like B, the capital B matrix. And yeah, so 10 times A is equal to my B example. I could say B minus A10 to show you. And then, yeah, so B minus 10 times A, yeah, that's equal to the 0 matrix, so that shows they're equal. And yeah, you know, I could do as well, I could do the equal, the logical equal, and that gives me the 3 by 3 matrix of logical truths. Remember, you have to be careful about that one. I said that in the very first video that I gave you. So I'm really very careful because it has to equal exactly from a floating point perspective, and you might miss out on that. So that's why I do this type of thing instead, to look how close they are. For maybe a commutative type of test, you know, I could do an A plus B type of thing, and then I could show that, yea, verily, that equals B plus A. Subtract off the answer there, and you see it's a 0 matrix. So you can see that, yeah, it's commutative. And then I can bring in a third matrix, a third 3 by 3. So these are all 3 by 3 matrices. And then I can show that, you know, you've got A plus B, quantity plus C equals a thing. And then I could show that A plus quantity B plus C is the same. Subtract off the answer, you should get the 0 matrix. Yeah, so it is commutative as well. So in preparation for showing you matrix multiplication, I wanted to print out a pair of matrices so that you could kind of see them side by side. And in order to do that, you know, like if you have a matrix A, I want to just print the dang thing. I know there's multiple ways of doing this, but let me show you kind of my adventure in this particular thing. I thought if I did this kind of thing here, so it's integer matrix, so I thought, well, okay, I'll do, you know, field of 6, floating point with dot 0 means no decimal shown. So I thought, well, you know, I should be able to do this. That's a formatted print. I should be able to print that, and yeah, it should print, you know, it should do 3 rows of A. But you know what? So it shows, it actually prints a 3 by 3, but it's, you know what? It's the transpose. And the reason it is because Matlab stores things in column format. So its memory shows is stored as 147, so that when I print it out 3 floats, it actually prints it out as the column first. So doggone it, you know, for me to print that A matrix, I actually have to show it in the correct way, I actually have to do the transpose. And I want to show you this tick as the transpose. So that tick right there, or apostrophe, is necessary in order for it to print the A matrix like I want. So the A matrix looks like a 1, 2, 3 first row, and a 4, minus 5, 6 second row, 7, 8, 9 third row. So for me to do that print statement, I need to do the transpose. And the transpose operator for a real matrix is an apostrophe. And I want to highlight that for a moment. Technically speaking, the tick, the apostrophe, the prime by itself is actually the complex conjugate transpose. So, or usually if you're dealing with real, it wouldn't matter, but I just wanted to highlight that that tick, that prime, the apostrophe by itself is the complex conjugate transpose, as opposed to the normal transpose that's shown as a dot tick or dot prime or dot apostrophe. And sometimes I see this dot notation in Matlab before an operator, and I can tell you that gets me really nervous. But the transpose, the ordinary transpose, where it does just swap row for column, interchange row and column for a matrix, that's the non-conjugate transpose that does that. That's the dot dot tick or dot apostrophe. Let's go take a look at that a little bit. So if I take A prime and look at it, and if I take A dot prime and look at it, yeah, they look the same because, you know, they're both real matrices, and I can show you again. I'm going to do a dot prime right there, A prime minus an A dot prime, and yeah, it's 0. Now, if I happen to go in and tweak one of these things and make, let's say I make let's say I make the 2, which is going to be first row, second element. Let's say I make that 2 plus I. Okay, so now it's printing it out like this. So only this one, only this first row, second entry is a complex. Everything else is actually real. Now when I do an A prime, I get where the rows and columns have interchanged, but it's also giving me the conjugate of the original 2 plus I. And if I go A dot prime, it's going to keep the original SIGN when it does the row column swapping. The dot prime is going to give me, it's going to keep that original sign on the imaginary part. And just to drive this home again, I'm going to do an A prime minus an A dot prime. And you're going to see that, that you're going to get that minus 2i down here as being the only difference. So just a strange thing. And I'm going to change my 1 comma 2 back to 2. Go back to the real domain here. It's a strange thing, but I wanted to show you that if we're dealing with real, everything's real, we could just use the prime. So where I'm going with this is I'm trying to give you a really good look where we can look at A and B kind of side by side like I had in the PowerPoint. I know that there's a concatenation operator that should kind of put them together side by side so I could look at them. Yeah, there's my A, here's my B. I kind of wanted to show it where you kind of see that labeled as A and that labeled as B. Yeah, that's right, row, column, everything looks right there. And then when I try to do the fprintf, I'm going to go A, and then, you know, like a %6.0f. See if I can maybe copy that. 3. And then I'm going to do like a vertical, or maybe, yeah, vertical bars to kind of separate. 2, 3. So that should print row by row. And then I can do the A comma B thing again, but remember, it's going to want, I have to put that tick because of the way fprintf works as it goes into the way the matrix is stored. So I'm not really printing the prime, I'm not really printing the transpose here, I'm actually printing what I want. So yeah, it looks like A is looking there, 1, 2, 3, 4, minus 5, 6, 7, 8, 9. And then B is over here is 10, 20, 30, 40, minus 50, 60, 70, 80, 90. So that all looks good. So the matrix multiplication here that I spoke of earlier is done with the star. So A star B should be my matrix multiplication operator, and we're going to check. We're going to kind of dive in and check this to make sure. For example, first row dotted into first column. So that's why I wanted to print it this way. First row dotted into first column. So that should be a 1 times a 10 plus a 2 times a 40 plus a 3 times a 70. Let's see what that looks like. So that's that row dotted into that column. And let's see if that's 300. It is. So let's take another one. Let's take, for example, the third row dotted into the second column. Third row, 7 times second column would be 20. And then I need a, I've got an 8, but then I've got a minus 50 there. So I'm going to say minus 8 times 50. And then I have a plus 9 times second column 80. Just double check. So I've got 7, 8, 9, 7, 8, 9. And then I have a 20 minus 50 and 80. 20 minus 50 and 80. Yeah, so that's third row, second column should be third row, second column here. So that should be 460, I think. Let's see. It is. And I think you could go through some of the others if you like to see that, yeah, it does work. So in this example, we did a 3 by 3A matrix and matrix multiplication with another 3 by 3, and the result was a 3 by 3. And it just so happens that we could do an element by element multiplication. Very rarely do you do this, but I wanted to show you, and the reason I wanted to show you is this quirky dot notation. See, we've got a dot star. So A dot star B is an element by element multiplication of A times B. Let me scoot it down just a hair. So what that means is you would do that 1 times 10, and that would be the 10. Then you did a 2 times 20, and that would be a 40. and then you do a 3 times 30, and that's your 90, and so forth. 8 times 80 is 640. So that's element by element. That's that dot star. The parallels for the consistency with the dot notation in Matlab, that leaves me a little uneasy, very uneasy. I'm not a big fan of that, but anyway, I wanted to show you that, something you very, very rarely would use. And I think I've called this the Hadamard, very, very rarely, Hadamard product. That's what I call it. That's where you do the element-wise product, very rarely. And for that, you do need that. You do need the matrices that you're multiplying, the dot stars. Those have to be the same size, exactly. But the matrix multiplication, you just needed the number of columns of the first one to equal the number of rows of the second one. Okay, I wanted to investigate commutativity with you, and to do that I thought I would create a new matrix D that wasn't simply a scalar multiple of the original matrix A, and to prepare to multiply them, I thought I would show you the two matrices side by side, A and D like that, and then here I'm kind of set up to multiply A times D, so the 30 here should be 1, 2, 3 times 9, 6, 3. So that should be the 30 and so forth. So that product, A times D, the matrix multiplication like that, should not be the same as where I might swap D and A around. It's not commutative. Let's see what we get. So if I were to print D times A, two matrices side by side look like that. Let me go D times A now. And the first element is 90, so that 90 would be 9 times 8, or 987 dotted into 147. So you can see that the two are not equal. So it's not commutative. Okay, let's take a look at maybe some associative property for multiplication. And you know what? Maybe I do a new matrix, maybe a 3 by 2. Let's do maybe a 100, a 150. Then we do maybe a minus 200, maybe a minus 100. And then maybe a 50 and a 75. What the heck? See what that looks like. Okay, so I've got a 3 by 2 and A. Let's see what the size of this looks like. If I take A and maybe combine D and E, those three, and put them into a cell array, I can at least see what their sizes are. So I'm going to look at doing an A times D times E. So if I happen to do the multiplication of A times D, and then do E, what do I get? Boom, get that mess. All right, let's see if how that ports with an A times quantity D times E minus answer. See if that's all zeros. It is. So just showing you that, yeah, associative for multiplication does work. If I take a look at how these sizes sort of played out here, remember A was a 3 by 3, D is a 3 by 3, E is a 3 by 2. Multiply the 3 by 3 times a 3 by 3, you get a 3 by 3. Take that result, multiply by a 3 by 2, you get a 3 by 2, and that's what we ended up with. A lot of 3's in here, and I thought, what if I were to change A and D up a little bit, and I made maybe A a 3 by 4, add a column to A, and then if I were to add, I'd have to add a row to D in order to multiply those together. So a 3 by 4 times a 4 by 3, I think I said that right, but let me see. So if I say, okay, maybe just say I don't know, x equals 1, 1, 1. So what does that look like? That's a row vector. What happens if I do x prime? Yeah, it makes it a column vector. And I wanted to add a column to A. So I'm going to say A1 equals the original A, and then I'm going to add on, concatenate that column vector. And yeah, so that's made me a 3 by 4. So I've got A1, and then I'm going to say D1 is going to be the D, and I want to add a row, so instead of concatenating with a comma, I'm going to do semicolon, and then I'm going to go with an X, because that was the row, just the X. See what that looks like. Okay, so I've added the one down there. Now, if I go and look at that cell array, I just do this so I can see the sizes, like that. Oh gosh, no, I needed A1, D1, and E. Yeah, so there's the 3 by 4 times a 4 by 3. That would give me a 3 by 3. And that result, I could multiply by 3 by 2. Let's see if it works. So I could do A1 times D1 times E. See what that looks like. Yeah, so it gives me a 3 by 2. And of course, you know, different answer than what I had before. I don't think that I even need any parens since it's associative. Yeah, so there you go. So very nice. Just wanted to change it up a bit. Okay, I wanted to take a look at inverses now. So I have my A matrix, and I may want to call my inverse of that AI. So I'll do that, and I use the inv function, and I'll put it in there and see what I get. So I get a matrix, AI, and that's supposed to be the inverse. Let's see. So if I do A times AI, what do I get? Okay, there it is. There's the multiplicative identity. The identity matrix right here. This is the multiplicative inverse of A. Well, if you're like me, you kind of wonder, well, what is the inverse of the inverse? So I'm going to go AII equals the inverse of AI. Just wondering what that is. Hey, look at there. I wonder if that's actually equal to A. So AII minus A. Oh, it's showing 10 to the minus 14th times a 3 by 3 matrix. So this is really, considering floating point round off, this is very, very close to a 0 matrix. The inverse of the inverse is equal to the original matrix, it looks like. And if I were to say AI times A, in other words, swap them around so they're mutually the inverses of each other, then you see that, yeah, it is the identity matrix. So they are mutually the inverses of each other. Well, so far we've accomplished 2 of our goals. We took a look at some matrix algebra theory, and then we went and took a peek at Matlab to see what all that looked like. Now we're going to take a look at our first linear system. And remember, when we put our linear system in a normal 3 independent equation type of form, it looks like this. And for my example, I've put in some numbers for the A and then the B vector. And then over here, you put it into a matrix format. So you have your A's coming out, and you have a column vector of X, and you have a column vector of B's. And I'm going to keep that same A in the example that I had before, and I've created a different B vector here, and I'm going to let that equal 10, 20, and 30. And I'm looking for the x1, x2, x3 that will satisfy this matrix equation, and will also satisfy the 3 independent linear equations. And if you write that in a focused view of an algebraic system, sort of writes like this. Sometimes you see x and b given in bird wings, but I like to show them as under bars. But how this should work, you should be able to see that if I multiply both sides by A inverse, then the A inverse A on the left-hand side is going to change to an identity, which will be the same as x. And then I end up with this A inverse times the B. So this is a solution to the problem. Let's go check it out in Matlab. Okay, so now I'm ready to sort of investigate this linear system. So there's my A matrix. There's my B vector, 10, 20, 30. So if I say x equals inverse of A, matrix multiply B, what do I get? Wow, it looks like I get 0, 0, and 3 1/3. Does that sound right? I have two entries as 0, and then that 3 1/3. Well, you know, one thing I could do is say A times x, that should equal B. So what happens if I do AX minus B? Yeah, you get that 10 to the minus 14th again times something. Or I could just say A times x to see what it looks like. It is 10, 20, 30, so it does look like that's correct. The 0, 0, and then 3 1/3. Let's go back and look at the original problem. If I look at the original problem, what it's telling me is I've got a 0, 0 for x1, x2, and then I have a 3 1/3. Well, if you look, the third column is proportional to the B vector. So 3 times 3 1/3 is 10. 6 times 3 1/3 is 20. 9 times 3 1/3 is 30. So it just worked out that it does go 0, 0, and 3 1/3 because of the way the B vector was with respect to the A. So I thought I might change it up a little bit and change the B2 from 20 to maybe a minus 20 and kind of recast this and see what I get. So when I go and look at it in Matlab, I'm going to say B, the second B is going to be equal to minus 20. And then I'm going to go and do, I'm going to say, let me call it x1 equals inverse of A times my modified B. So now, yeah, I get some non-zero things in the first entry. And then if I do A times x1, yeah, I get the 10, the minus 20, and the 30. And if I were to say, okay, minus B, I do get that, see that minus 10 to the minus 13 times that little bit of a vector there. So interesting. So as I was saying, it's kind of tough to say, okay, does A times that x1, does that actually equal B? The zeros here means false, 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 that they're not exactly equal because of round off. Very, very close to being equal, but they're not exactly equal. Again, this is a good example of why I say to do it this way, where you go A times x1 minus B to show that 10 to the minus 13th times those entries right there. So looking at what that solution x1 vector is, a minus 2, a 4, and a 1 1/3, when I bring that back and look at putting them into the positions there, that A matrix times that solution vector, yes, that will equal the 10, the minus 20, and the 30 I did for the tweaked example. So it looks like we've kind of achieved all of our goals. We looked at that last thing, the first linear system, with an actual tweak. So we've covered a lot today. I hope you've enjoyed it.